Hello, my name is Gladys Sandoval, and today I will be showing you how to create a proof for a problem. I will be talking about problem 4, which states that for all integers m and n, if m is odd and n is even, then 4 does not divide 2m squared plus n squared. An example that proves this is by letting m equal 3 and n equal 2. Then 2m squared plus n squared equals 2 times 3 squared plus 2 squared, which then equals 22. And 4 does not divide into 22. A few words that you will see here are divides, even, and odd. Divides just means that if you let a and b be integers, then you can write a and then a slash b. And you just read that as a divides b. And if there exists an integer q such that b equals aq. Even is an integer n, and then if there's an integer k so that n equals 2k. And odd is also n, and then the integer k so that 2k plus 1. So 2 times a number will equal an even number, and then 2k plus 1 equals an odd number. So if we look back at the problem, it's quite difficult to try and prove straightforward, so we will try to prove it by the contradiction. The contradiction of the problem is that there exists integers m and n such that m is even, n is odd, and 4 divides 2m squared plus n squared. In order to organize our proof, we will create a no-show table, which points out all the points that we need to provide in the no-show table. So as you can see, we begin by writing the steps on the left side. We write down what we know in the middle, and then we write the reasoning for what we know on the right-hand side. And we're going to begin with the hypothesis, which is basically just a contradiction. So there exist integers m and n such that m is even, n is odd, and 4 divides 2m squared plus n squared. From there, we will write the definition of even and odd. So we would write that as there exists integers k and j such that m equals 2k and n equals 2j plus 1. As we previously spoke about even, we saw that 2k is even and 2j plus 1 is odd. From there, we will write the definition of divides since we're talking about divides up here. So we would write that as there exists an integer q such that 2m squared plus n squared equals 4q. And that's just rewriting 4 divides 2m squared plus n squared so that we have an equal sign instead of a divides. From there, we will substitute for m and n, giving us 2 times 2k squared plus 2j plus 1 squared equals 4q. So we just plugged in the even and the odd, and then we wrote it in the equation for definition of divides. From there, we're just solving for the left-hand side, so we get 16k squared plus 4j squared plus 4j plus 1 equals 4q. And then if we divide out a 2, we get 2 times 8k squared plus 2j squared plus 2j plus 1 equals 2 times 2q. And if you can see, if you substitute all of this right here for a j, it's the same thing as 2j plus 1, which is right here. And that's the equation for odd. And then over here, it's 2 times 2q. And if you substitute 2q for a k, then it equals this right here, which is an equation for even. So from there, we can see that odd equals even. And because we did it by proof of contradiction, there is nothing to show at the bottom because we weren't really solving for a conclusion. We weren't trying to get to a conclusion except for odd equals even. After creating the no-show table, you will go into writing your proof. So, because in the problem we know that m and n are integers, we will state that we're letting m and n be integers. From there, we'll write the proposition, which is m is odd and n is even. And then you will write what we are proving for. So in this case, we are proving that 4 does not divide 2m squared plus n squared. But since that cannot be proved for, we will be stating that we are using the proof of contradiction, and then that by the proof of contradiction, we are saying that there exists an integer m and n such that m is even, n is odd, and 4 does in fact divide 2m squared plus n squared. So when writing a proof, you always want to state how you're proving your statement. Unless you're doing a direct proof, then you don't need to include how you're proving it. So as you can see, this part right here was our hypothesis in our no-show table. And then from there, you're just going to follow the order. So because the next order was the definition of even and odd, we're going to come down, and after the hypothesis, we include that there exists an integer k and j such that m equals 2k and n equals 2j plus 1. And that's by the definition of even and odd. The next step is the definition of divides. So here you can see that we include that there also exists an integer q such that 2m squared plus n squared equals 2q by the definition of divides. After that, we're going to substitute for m and n, which is what we do down here, and we'll write out all the algebra the same exact way we did over here. And this is a sentence entirely as well, so when you end the equations, you want to add a period at the end. And whenever you write equations in your proof, you want to line them up by the equal sign. From there, we are going to include that since the integers are closed under addition and multiplication, then 8k squared plus 2j squared plus 2j and 2q are integers. I got these numbers from what's in parentheses at the end of the algebra. So what's in parentheses here and what's in parentheses here. Then we can see that 2a plus 1 equals 2b, where a equals 8k squared plus 2j squared plus 2j, and b equals 2q. Again, I just substituted the a for what's in parentheses here, and the b for what's in parentheses over here. And we can see that this becomes 2k plus 1, or I'm sorry, 2a plus 1, as I stated over here, equals 2b, which is the same thing as over here, 2k plus 1 and then 2j plus 1, just with different integers. But we know this is even, this is odd, same as over here, this is odd, and this is even. So that's when we come to our conclusion that odd equals even by the definitions of even and odd. Thank you.